Hello everyone. Myself Dr. Rajesh Prasad, working as professor in Ajay Kumar Garg Engineering College, Ghaziabad. So I'm going to discuss closure properties of regular languages. We know that regular languages are a special class of languages which are accepted by the finite automata. So this is the content which I'm going to discuss, and this is we are going to discuss core operations, right? So core operation will cover union and concatenation, clean closure, intersection, and complementation and reversal, right? So we'll see that finite automata are closed under union, right? And the finite automata are also closed under concatenation, meaning that if we are given two finite automata, right, two finite automata, that can be DFA, that can be non-deterministic finite automata. So their union will also be DFA, right? Similarly, if we have one language which is accepted by DFA and another language accepted by DFA L2, then their union L1 union L2 is also going to be regular, right? It is also going to be accepted by DFA. Same thing with concatenation. If L1 is language L1 is accepted by DFA regular and another language L2 is also accepted by DFA, then their concatenation L1.L2 is also going to be accepted by the DFA. Same thing is here with clean closure, which we call it star closure. If L1 is a language which is accepted by DFA, then its star closure is also going to be accepted by the DFA. Next is intersection. Same thing here. If L1 is like a language which is accepted by DFA and L2 is a language which is accepted by DFA, then their intersection L1 intersection L2 is also accepted by the DFA. That means it is also going to be regular. Same thing complementation. If L1 is language which is accepted by DFA, then its complement L1 complement is also going to be accepted by DFA. Reversal is also which we call it transpose. If L1 is language which is accepted by DFA, then its reversal is also going to be accepted by DFA. So these are the content which we are going to discuss. So let's discuss the union operation, right? So very fundamental diagram. So we are assuming that this is the like a language, right? Suppose this is language 1 and or this is accepted by the machine M1. Since it is regular, we assume that L1 is regular, L1 and L2 are regular languages, right? So that means this is accepted by DFA. So it has a starting state and it has final state, right? This has a starting state, this has a final state, and there may be like many transitions inside the machines, right? Similarly, we have another machine, let's say M2, okay, and its accepted language is L2. So its starting state is, let's say, Q2 and its final state is F2, okay. So we make like this, clear, and this is F2. So in order to get union operation, what you will do, let's add another separate state, we call it Q0, and let us have another final state which is not in the original list of final, make it the final state, right? These are the two additions of state. From starting state by epsilon, go to the starting state of this. By this one, go to starting state of this by epsilon transition. So by this epsilon, you go to starting state of this. By this, go to starting state of this. See this? And of course, you know, if this is accepting, let's say L1, so if you follow this path, right? If you follow this path, it will accept L1. If you follow this path, it will accept L2, like here. Epsilon dot L1 dot epsilon. That means still it is accepting L1 by this way. Similarly, if you go by this way, epsilon dot L2 dot epsilon, it is accepting L2, right? So that means this is actually like machine for LM1 union LM2. So we can see that since individuals are finite automata, their union is also going to be finite automata. So very simple construction, right? So that means we can say that, okay, union of two finite automata is also a finite automata, only adding 4 transitions and 2 additional states, right? So next one is like concatenation. Same procedure we are applying. Suppose this is a machine number 1 and corresponding language is L1, and this is machine number 2, okay, and corresponding language is L2, okay. And now this is Q1 and this is F1, starting state of this and final state of this. We have many intermediate transitions, right? Similarly, Q2 is this and F2 is this. We have many intermediate transitions over here. In order to get the concatenation, make this as a final starting state. From the final state of first machine to the starting state of the second machine, make a epsilon transitions, right? And make this final state as a final state. So you can see that this is accepting, let's say, language accepted by machine 1, and this is language accepted by machine 2. So of course entire like diagram is accepting LM1 dot LM2. That means of course this individual is finite automata, so entire machine is also finite automata. So we can say that concatenation of two finite automata is finite automata, right? So third one is a Kleene closure. And remember, this is unary operator, unlike concatenation and union. So let's see, this is a machine which is like, let's say this is machine number 1 and it is accepting L1, okay. And its starting state, let's say Q1, okay. And its starting final state, let's say final 1, okay. So let's say this is Q1 and this is F1. Now, in order to get its repetition, okay, what you will do, just like take new state as a starting state, clear, and then take another state as a final state. 2 additional states we are going to include over here, right? So from starting state, take 1 epsilon here, and from here take another epsilon. This epsilon will make sure that it is accepting epsilon. Look at here. Like see, if we are talking about L star, this is epsilon plus L square plus like that, right? Or you can say that epsilon union L square, this keep repeating. So that means minimum is epsilon. So by doing this, it will go and accept epsilon. If you go by this way, epsilon, and then you want to repeat, finish it, go by epsilon, and from final state to this, take another epsilon. So we can say that this is actually repeating L1. See how? Suppose you want to generate epsilon, it will generate epsilon. By doing this, it will generate epsilon. You want to generate L1, go by this epsilon, okay, and then one time this is accepting L1, and then this is, you are finishing by epsilon, so this will take L1. You want to repeat it again, so take one type of epsilon L1 and then take it back by epsilon, right? So again epsilon, then take L1 and then take again epsilon, so it will keep L1 square. So this is very simple construction. You are only adding two states, Q0, Qm, and 4 additional transitions we are including, right? So epsilon, this epsilon and this epsilon and another state epsilon. So by doing this, we can say that finite automata are closed under Kleene closure, star closure. Is very simple. Okay, so let's have like one yes. So let's have like this in another one. Like, see, if you want to make a machine for 0 plus 1, okay. So it's very simple to construct a machine by using this method. See, this is machine which is accepting like 0, okay, and this is machine which is accepting 1. Clear? This is machine which is accepting 1. So now by using this construction, take another state and take another state. Okay, take it epsilon and take it epsilon and take it epsilon and take it epsilon, right? So you can see that and this is final starting and this is final. It's very simple, just rename it Q0, Q1, Q2, Q3, Q4, Q5. So you can see that epsilon 0 epsilon or epsilon 1 epsilon. So of course this is accepting 0 plus 1. Okay, so yes, so in order to make it 0 plus 1 plus 2, make sure that we are constructing 0 plus 1 first. Then take another machine for, let's say, Q2, 2. So take this as a 2 machine, right? Because this is a binary operation, it can only be done like for 2 operations only. So now this add another state and add another state. Starting to this epsilon, starting to this epsilon, is final to this epsilon, final to this epsilon. This is no more final and this will become epsilon. So this is also going to accept this 0 plus 1 plus 2. Similarly, for intersection, this is also important. Just like if you want to accept 0 dot 1, what you will do, make a machine for 0 here. So it is 0 and then make a machine for 1. Okay. So make a machine for 1. From here you just take epsilon and this become final starting state and this become final state. So this is also important. Similarly, if you want to take, let's say, I'm interested in 0 star. Okay. So it's very simple to construct machine for 0 star by using Thomson construction. We call it Thomson construction. So make it 0 here. Take additional starting state, take additional final state. From here you take epsilon, from here you take epsilon, from here you take epsilon, and from here you take epsilon. Right? So you see this is the same method. This is the starting state and this is the final state. So by doing this, you can say that this is actually accepting 0 star. Epsilon is accepted. One time 0 is repeated, 2 times you can go and repeat it. So it will accept the 0 star. We know that another way of accepting 0 star is just like this, but this is a shortcut notation to accept 0 star. This is not using our construction. Okay. So next important thing is that intersection. That means, if L1 is one machine and L2 is another machine, so if you want to take their intersection, you will see that L1 intersection L2 is also like DFA. This is very important examples of taking intersection machine. Suppose we are interested in designing a machine like M1 is like all string, okay, over 0, 1, accepting like even number of 0, right? M2 is another machine, all string over 0, 1, right? Accepting even number of 1. Okay. So if we are designing a machine which is accepting even number of 0, right? It's even number of 0. Means this is going to be 0 to the power 2k. This means that 0, 0, 1 can be here, 1 can be here, 1 can be here, and this can be here. Okay. So this is machine for even number of 0. Similarly, if you take this M2 is a machine for even number of 1, that means it will take 1 to the power 2k, right? So 1 1, then this can be 0, this can be 0, this can be 0 and star. So if you see here, if you take machine M1, you know how to construct machine 1. Take the shortcut notation, right? So let's say this is Q1, and since it is accepting final, so this is final, and then 1 and then 0 and then Q2 and then again 1 and go back and say 0, and this will accept the even number of 0, right? Even number of 0. Now let us have another machine which is accepting even number of 1. So this is like, let's say Q3, okay, and this is 0 and this is 1 and then this is Q4, and take it 0, right, and then this is 1. So now you have another machine M2. So this is machine 1 which is accepting even 1, even 0, and this machine is accepting even 1. So if question is that construct a machine which accept even A and even B, right, and even B, even A and even B. That means this and is not going to be for concatenation, it is going to be for intersection. So it's very simple to construct the intersection machine, right? Just take like Q sigma, this is 0, 1. You see here, and number of state in intersection machine will be 2 state here, 2 state here, it will be 4 state. So what you will do, take Q1 combine with Q3, okay, then take Q1 combine with Q4, right? Take Q2 combine with Q3, take Q2 combine with Q4. Clear? Yes. Take first combine with all state of second machine, take second combine with all state of second machine. Starting state will be the one which is starting in both the one. So this is starting. Same thing, final is also present in both. So this will be final, right? So Q1, Q3 on 0 means Q1 0. Q1 0 you are getting Q2. Q3 0. Q3 0 you are getting Q3. This is state, right? Similarly, Q1, Q3 1, Q1 1 is Q1 and Q3 1 is getting Q4. Clear? Q1, Q2, Q4 1, Q1 0 is Q2 and Q4 0 is Q4, right? Yes. Q1, Q4 1, Q1 1 is Q1 and Q4 1 is Q3, right? Yes. Q2, Q3 0, Q2 0 is Q1 and then Q3 0 is Q3. Yes. And Q2, Q3 1, Q2 1 is Q2 and Q3 1 is Q4. Yes. So similarly here Q2 0 is Q1 and Q4 0 is Q4, right? Yes. Q2 1 is Q2 and Q4 1 is Q3. So this is intersection machine for the individual machine. Complementation is very easy. That suppose this is DFA. Remember, complementation is possible only for DFA, right? Yes. So this is, let's say, DFA. Okay. Let's say this is 0, this is 1, and this is 0 and 1. So complementation machine is just like making final to non-final and non-final to final. So this is non-final state, make it final, okay? And this is like a final state, make it non-final. Only like changes we are going to have. Final to non-final, right? And non-final to final. That is only changes in complementation machine. Clear? Yeah. Okay. Reversal is like a transpose. This is also like very simple, right? If you have a DFA, let's say DFA Q1 and Q2, right? So this is reversal like 0 and let's say 1. This is 0 and 1. Its reversal is just like transposing the arrow, right? Just transposing the arrow. So this is like this remain the same. Okay, and this will be 0. Okay, and this is how we are going to have, right? Yes, reversal machine. But remember that this was the starting state, so now this is like this will be the starting state. This is not going to be starting state. We can say that just like transpose, that reverse of DFA is also DFA. So these are the references: John Upcroft and KLP Misra and Peter Lynch. You can see them. Thank you.